Once you've pressed Simulate and Plot, you'll be met with this menu, which will enable you to plot graphs and export the data generated during your simulation. By default, the Plot Data tab will be open, which allows you to create graphs. And by default, again, a vertical motion versus time graph is set up. Any graph can be set up using X and Y axis components and then marking flight events. The X-axis can be any variable you wish. We're going to leave this as time. And the units can be in seconds or minutes for time. The Y-axis can then be as many or as few types of data as you wish, and you can set up where the axes for that data is displayed using the axis. We're going to leave the default altitude, vertical velocity, and vertical acceleration. To the right, you can see the flight events, and you can select and deselect these to see them shown on your graph when it's output. We're once again going to leave the defaults. We're going to press plot. That gives us this graph here. As we can see down the bottom left, we can choose to display data points, which will show us each of those steps that have been calculated by OpenRocket. Although we're going to leave this off because this makes it more challenging to look at. If we want to use this graph, we can export the image and then save it anywhere on our computer we want as a PNG file. We can also, if we wish, export our data as a CSV file, so something interpretable by Microsoft Excel. And to do that, you can select any or all of the variables you wish. You can set your formatting, you can set comments, and then you can hit export. Another type of graph we may want to have a quick look at is a stability versus time graph. So to plot one of those, we're going to reopen our simulation. We're going to move down to the preset plot configurations drop down, and then we can move to stability versus time. If we plot this as a graph, we get this, which shows that the stability coefficient of the rocket varies with time in an expected manner. Obviously, as the mass of the rocket decreases due to the motor burning out, the center of gravity of the rocket will move forwards, which is the reason that there's an increase in stability coefficient. As the rocket then slows down vertically and reaches a minimum vertical velocity at apogee, the stability coefficient will decrease due to a reduction in airflow over the rocket. We're not too interested in the stability of the rocket beyond that, although this shows that the rocket is reasonably stable in flight beyond that. As you can see, if we zoom to this point on the graph, this green line, the launch rod clearance, there is an initial stability coefficient of 1.4. If we are operating on a minimum basis of 1.5 as a stability coefficient, this would not be acceptable. It's also important to note that this is wildly different from the stability coefficient given in the viewer menu of 1.78, which is a measure of the static stability of the rocket, so the distance between the center of pressure and the center of gravity divided by the diameter of the body tubes.